Okay. Among the humans, right, and men and women, but when it comes to the prostate cancer, it's the second common in the men. Okay, so the risk factors include age. Surprisingly to me, it's family history and race. And what we know about prostate cancer, it's extremely slowly growing cancer type. So it is almost impossible to detect this cancer in its early stage. When we talk about this, it generally affects the men over 50 years old, and so that's why, because of its location and so on, it limits the efficacy of the chemotherapy. Okay, so most of the time, so sometimes it can be applied. I'll talk those cases, but most of the time, chemotherapy is not applied to treat this type of cancer. So usually the men over 50 years old, they are suggested to go through the screening. So since we said it's the androgen level is important, so what they do is they look at the so-called PSA level, which stands for prostate specific antigen. Okay, so they look at this level, and if it's high, it doesn't necessarily mean that you have a prostate cancer, but it might be one of the signs. So that's why, like, because I mean, sometimes people have like high androgen level, and they can have no cancer at all. So that's why it can give you false positives and negatives. However, if the prostate cancer is detected in its early stages, it can significantly reduce mortality rates. So that's important to go through the screening regularly. So how do you to verify this presence of a cancer? So if the PSA level is high, so how do you verify if somebody has a prostate or doesn't have? So at the end, of course, to make sure medical doctors do a digital rectal exam. So if you don't have questions, I will ask you to mute your mics. Whenever if you have questions, feel free to ask any language, as I said. So what they do is they of course at the end do a rectal exam, and that's the only way to, and they take a biopsy. Okay, so based on this analysis, only they can understand if a person has a prostate cancer or doesn't have a cancer, given the high level of PSA levels, high level of PSA. So when it comes to the incidence rate, okay, so this is, I took from cancer report from 2012, I'm sorry. It's a 10 years old report, and I haven't found recent reports. So that's why this 10 years old, but I don't think there is a significant change in terms of these statistics. So when we look at this age distribution incidence rate, then we see that, surprisingly to me again, Western countries and Western Europe countries, more developed countries, have higher incidence rate than compared to, let's say, our countries like Central Asian countries, Turkey, and some Middle Eastern countries. Okay, so that is something I have no question like answer, but that's what the statistics says. Okay, so this might be, in my opinion, about how we work and our living culture. Okay, so that's just a guess. But I have no clues. Okay, so when it comes to, however, the mortality rate, so it's our countries maybe with some exception of Turkey, is almost the same like with the other Western countries. Okay, so so I can see that here, like Turkey has a little bit higher mortality rates than other countries in the region. Okay, so although we have low incidence rate, but when it comes to the death rate, unfortunately, it is the same. So what kind of treatments available to treat this kind of disease? So so if it is detected in early stages, then that's it. If it is localized cancer, then what the doctors do, they wait and they do active surveillance. Okay, so and then if it starts to grow, they remove the cancer. Okay, it's a surgical operation, like and if that is not possible, then after all that so after the removal they do radiation therapy. So this is the standard procedure if this type of cancer is found in early stages. So however, if that has advanced already, and even in some cases it become metastatic, what happens is that here, like they do some sort of which is called an androgen therapy, which is known as the hormone therapy or androgen ablation therapy. So this is still remains the main treatment for advanced prostate cancer. Okay, so that's some sort of so I would call it a hormone therapy, actually. Okay, so that so there's some chemical therapies, but this is not common. This is usually after the cancer has developed treatment resistance to hormone therapy. Okay, so if this, so for the advanced cancer, if hormone therapy doesn't give any result, then doctors may try chemical therapies. Okay, so, but that's not suggested. Something suggested. So, what is this androgen deprivation therapy? So that is to eliminate the androgen so that you eliminate the prostate cells, because we know that we said like prostate cells are like these are depend on the androgen level, right? Mainly those are testosterone as far as we call. So if you eliminate this androgen, prostate cells doesn't grow, and as a result, you localize the cancer. So other like what happens is that then you just can do surgical castration once it's small, and more commonly you just continue with, nowadays you can continue with androgen deprivation drugs. So you take these drugs, these hormone drugs, okay, which affect your hormones, then it just eliminates your androgen level. So it does have, however, side effects. So like short-term side effects are like sexual dysfunction, hot flashes and fatigue, and long-term, among long-term effects, you have osteoporosis, muscle loss, anemia, and etc. Okay. So I'd like to here talk about like androgen-independent relapse. So this is also possible, like one of the treatments. So what happens is that so how this therapy is carried on. Okay, so once you take these drugs, like you eliminate the androgen level, then the prostate cells starts to shrink. Okay, so at some level, after monitoring, they stop this drug. Okay, so this treatment, because it has like side effects, as we talked already. You can't continue taking this treatment for a long time. Okay, so as soon as it gives you a positive result, as it reduces the number of androgen level, you stop this treatment before you say again this androgen independent relapse. Okay, so once it androgen level starts this PSA level starts to grow, then again you restart the treatment so to slow down the PSA level. So then you continue this treatment like in an on-no cycle in a repeated manner until the treatment is ineffective. So if it's ineffective, you try they try chemical therapy, and that's of course in a rare cases, but most of the cases this treatment is preferred. Okay, so because the advantages is that it gives a patients a better quality of life. You don't have like you don't go like through the chemical therapy, and the side effects of chemical therapy is worse than this one, right? So that's why because of this quality, it possibly delay the progression of this androgen independent cancer. So if you look at the example of the treatment, then it's like as I said, on and off treatment. When it's when the both testosterone and PSA levels are high, you switch on the treatment, and then you start to observe that both testosterone and PSA levels start to slow down, and it's almost converge to zero. Okay, so then you turn off the treatment, you stop the treatment, and after some time you observe the patient. If patient's testosterone level and PSA level start to increase, at that point you again turn on the treatment. So the treatment is just, you can start and end based on the testosterone and PSA level of a patient. So this is kind of a roughly like treatment protocol, I would say. Okay, so based on this treatment, we are going to model our. We're going to have mathematical model. So before we go to our study directly, I would like to briefly discuss about existing mathematical models before our study. And the early models go back to 1993 by York et al. Okay, so this is just a simple ODE model based on similar to Gompertz and Gross. So Gompertz Gross is a logarithmic growth function, which is commonly used in tumor growth models. Okay, so this is not just ODE model. Okay, so this involves standard treatments and show the early positive results. However, this model failed to contain tumor relapse after the cancer has metastasized, and that's the main shortcoming of this model. Okay, so then the next model I like to talk about is Swanson model, so-called PSA model. This is a continuous production rate. It takes into account continuous production rate of PSA level, and in this model, abnormality in the PSA represents of the prostate tumor volume. And then comes the Jackson model. So this is so the Swanson model is a PDE model, where Jackson model, Swanson model is an ODE model, where Jackson model is a PDE model. So it covers continuous therapy and predicts successful treatment for limited range of parameters. Yeah. So the model which our study is based on is so-called this E-data model, which was published in 2008 in Nonlinear Science. It's an ODE version of Jackson model. It takes into account this intermediate therapy that we talked about, this switch on and off model. Okay, so it predicts successful treatment only when androgen has negative effect on androgen independent population, so A population. Okay, so then there is Kashkynbayev model, which is really close to our model. So I'm going to refer to these models later on in our study. Okay, so when we So the difference of this study is that we had patients' data on open access, so that we could feed those data and do the error analysis at the end and compare all this analysis. And I'll show the result at the end about this. Okay, so Port's model. So our model is kind of based on this Port's et al. Model. So one of those co-authors of this model is this K stands for Yang is one of co-authors of our study. So at the end, I'm going to thank all my co-authors. And this is based on Jackson and Lidette models, and it has no negative effect on the androgen on AI cells. So if you remember, the Lidette model had this effect. So we are going to divide our population into two subpopulations. One is going to be X1, which is androgen dependent population, and another population which will be X1 in our model. And another one will be, another subpopulation is X2, which is androgen dependent. Okay, so one is androgen independent. I'm sorry, so this should be independent. I'm sorry, there is typo. So this X2 is shortly AI, androgen independent, and these ones are androgen dependent population. So the serum androgen concentration in the model will be denoted by A of T. Serum PSA concentration will be P, and cell quota variables for androgen will be like Q1 and Q2 respectively for X1 and X2. Okay, so the assumptions here, we assume that androgen independent population has increased sensitive to androgen. So this means that they can survive at lower levels, which is close to reality. So the PSA production is dependent on androgen. So as we talk in the first slide, right? Switching behavior between we can see in this model switching behavior between cell populations, and so this is how the model itself looks like. So so here I is just one or two. If I is 1, then J is 2. If I is 2, then J is 1. Okay, so since we have only two subpopulations here, so the governing equation for this subpopulation is, we assume that it grows logistically in the absence of the other. Okay, so the first growth factor is in fact logistic growth factor, and this one is we assume that this rate is some DI. Okay, and this one is cell transformation. Okay, so the transformation from cell 1 is a gain for cell 2, but it is vice versa for cell 1. If it is loss for cell 1, it is gain for cell 2, but the loss for cell 2 would be gain for cell 1. Okay, so this I's are not equal, I and J not equal to each other, and it can take either 1 or 2. Okay, so this is this Q is, if you remember, is for cell quota variable, right? So the cell quota was with this value here is to model androgen influx to cells. This one is uptake, where this one is clearance. Right? So the prostate level is going to depend on this PSA production level, and of course we also have prostate clearances here. We have at some rate. Okay, so so this we have PSA data. Okay, and unfortunately we don't have cell quota data. So with this model we can fit the PSA level, and you can see that like these ones are the blue ones are fitted data, and this red ones are PSA data. And we are dividing these AD cells like androgen dependent, independent cells. Okay, so these are given. And if you look at the PSA level, this model does a good job in fitting this patient-specific data. Oops, this is so there wasn't, so this was an existing study up to our study. So we took an alternative approach and applied fractional calculus, like fractional derivation. And the idea comes from, so I think everybody is here familiar with the fractional calculus and fractional differentiation. And there are many experts like Professor Ashirlayev here, Alabren Ashirlayev, working on this field, I know. And it has many applications in viscoelasticity, electrochemical chemistry, PDs and applications, control theory, mathematical epidemiology, neural networks, and we ask ourselves, can fractional calculus, these fractional models, can somehow improve so-called models in mathematical oncology, like these prostate cancer models in the literature. So what we did is we know that this fractional differentiation has an advantage in a way that it captures so-called memory effect. Okay, so the fractional derivative in time contains information about the fraction at earlier points. So so if you want to model the memory effect, you have other tools, of course, like making your model with delay, right? So it becomes an ODE model becomes a delay differential equation model. But once you have this delay term, the model becomes very complex. Okay, so it becomes hard to analyze, and here compromise, I would say, between making model very hard to analyze and getting no information and making it easy was like kind of to use fractional calculus. So so yeah, another like advantage of fractional calculus is it covers fractality, which is also common in nature. So uncovering patterns in nature, right? So it has multi-scale nature, and in our case, we have also seen that it's much better in fitting data too. So what we did here is that we considered the fractional model of PKN model. So that's the same model as before, but the order of fraction here, however, is unlike most of the studies we here take our fraction models can be different. Like the fractional derivative of x is not the same as the fractional derivative of the cell quota, for example. Okay, because you don't expect them to behave similar, right, in a similar order. So we considered different fractional orders that imposed extra difficulty, of course, but we were able to solve this problem. Okay, so then here gamma is this discontinuous function to cover on and off treatment. Okay, so the gamma is equal to gamma 1 times u plus gamma 2, where gamma 1 and gamma 2 are constant, and where u is just a step function, a discrete step function. Okay, so it's 1 when treatment is on and 0 when treatment is off. So this is one population fractional model. Here we don't distinguish between androgen dependent and androgen independent cell subpopulations. So X is for the total of two populations, okay, which with androgen dependent and independent. And this model is somewhat similar to the PKN model I showed before. It is two population model where this X population in the previous slide was divided into two subpopulations with androgen dependent and androgen independent cells. Okay, so here again we consider different order of fractional derivative. Like here size could be any value between 0 and 1. And yeah, here when we talk about fractional derivative, we talk in the sense of Caputo type fractional order. Okay. So so the dynamics, what we did is we first like proved that model 1, that's one population model, has 2 steady state solutions. Like one is cancer-free equilibrium solution because this X population is 0. And we were able to prove that it's locally asymptotically stable. Oh, I'm sorry, that has unstable cancer-free like equilibrium point. And there exists also local asymptotically stable endemic equilibrium point. Here, this is endemic because we know that this value is something positive, not equal to 0. Okay, so that's why this E1 is a steady state, and we proved that this steady state is locally asymptotically stable. So like when it comes to model 2, it has 3 equilibrium points. Okay, so one is again the similar one, the same as before. We have unstable cancer-free equilibrium point, which is denoted by this F0, which is unstable, of course. And in the case, this U stands for here when this function which covers the treatment, and we proved that if U of QM, where this QM is the cell quota, maximum cell quota is positive, or V of QM is positive, this cancer-free steady state is unstable. Otherwise, it's asymptotically stable. Okay, and there are 2 more steady states. One is cell only, CR cell only equilibrium point, which has like the first component 0 and the second component, this value is something positive. So it is asymptotically stable in the case when U of Q1 is less than 0 or V of Q1 is larger than 0. This Q1 is the minimum quota, and this QM is the maximum one. And there is some coexistence equilibrium point whose stability we couldn't prove. Okay, so but the existence was proved, meaning that this one and this value is something positive. So when it comes to the simulation of like fitting real data, these blue dots are data of patients, and we have like one population bias quant model, and we have like this red one, and the blue one and the green one is 2 population bias quant model. Okay, so these are without fractional derivative, and the black one is you can compare this with the red one. It's again 1 population BK model, but with fractional derivative, and 2 population. This purple one is the 2 population BK model, which is like you can compare to the green one. So in general, in all this patient data, we have seen that 2 population models fit data better than 1 population models. And if you compare among themselves, this 1 population models with its fractional analogs, we've seen that fractional analogs really can fit the data better than non-fractional models. Okay, so this integer order ODE models. So these are just you can see how we fit data with some given patients' data, and with, of course, like when looking at this data fitting, you might say that, okay, so I don't see like much difference between between these fits. Like then, of course, we carried out error analysis. So we compared mean square errors for androgen and prostate specific PSA for the first 1/2 cycles for BK model, and its fractional analogs. Okay, so if you look at these models, those ones which contain F is for fractional. Okay, so you can see that we improved the fitting abilities of these models compared to its integer order models. Okay, so in one population model, this significant, it is not much, but when you look at the two population model, we improve it by more than 10%. Okay, so yes, so here, like, these are for PSA level, and you can also compare here, for example, the maximum has been improved by factor of 2, and here minimum is not by factor of 2, but you can see significant improvement in androgen level as well. Okay, so so we were happy to see that these fractional models indeed do give us a good result compared to integer order models. And that is the end of my talk. Now, if you have any questions, I will be happy to answer them. And I think there is one in chat. Oh, I'm very happy to see you, Professor Weber. I know you all worked at METU when I was a student. I haven't taken your courses, but it's good to see you here.
I know you. You are my young professor.
Yes,
you are my young professor.
Thank you very much. Thank you.
Yeah, I was only writing that Ibn Sina is also from Central Asia. I was writing it. Ibn Sina is from. I wrote it in the chat.
Yes, I'm reading that. Ibn Sina is indeed coming from this region in Central Asia. Yeah, you're right. You're right. So he's famous for his studies in medicine. All right. So I can't compare myself to Ibn Sina, of course. So he's a great scientist, but we are trying our best. Like with the given data, we are trying to improve. So we said what we can do with the existing data, and it turned out to be that this fractional calculus helped us a lot in improving fitting ability of these models. Sureya Hocam, you have a question?
Yes, hello. I'm also one of the former students of Professor Weber. I was studied at METU. Nice to meet you, and thanks a lot for this very interesting talk. I took a course from Willis, Statistical Learning, and in that course, the first we have seen is that prostate cancer data. And as Willy knows, he can contribute also here. There are regression models. You may also aware of this from data analysis. So such data fitting methods like simple statistical methods also appear in the same type of problem. So you said that with this fractional differential equations, you also watched you consider the time. So you consider the previous time behaviors of the model. There are also existing models which considers time. So before, after, like time series models. Also, it exists in statistics. Recently, that I'm curious about what when you compare your results with LSTM, it is called long short-term memory methods from deep learning. So deep learning is very popular nowadays from artificial intelligence. My students nowadays, my graduate students, worked on this LSTM on stock market chains, some financial data, and it looks like your data appears lots of zigzags, lots of jumps, like stock market. I'm personally curious about the comparison when you apply. So where did you get the data? Do you have the original data set, or is it published? So maybe we can collaborate, contribute, and see the comparison, if the fractional gives better, or such LSTM gives better, or I don't know, maybe the joint contribution. My second question is, also recently, some of my colleagues has come to me and asked applying machine learning instead of solving numerical solution to PDEs, to see to make forecasting for the future. Instead of solving, they say, because there are in some of the physical problems, like earthquake problems, in earthquake, or in some civil engineering problems, they have lots of parameters that affects the solution of the problem. Instead of trying different parameters and solving the same system from scratch, it's time consuming. So instead of this, they asked me, how about to apply some machine learning tools to see the prediction. This is also exists. Some recently researchers started to do this. So also such methods can be replaced or compared with some differential equation models in future. Maybe just thanks again. Sorry,
Okay.
my question was a bit long. I'm just
okay.
excited about this applied problem. That's why I wanted to ask. Thanks.
Thank you. You have indeed very good questions. Right? So when it comes to the first question, like comparing this model to other models, so what we really had is so in our case, we looked at, I compared it with the ODE-PD models only. Okay, so and then we said, okay, why not to include some memory effect to this model? And that was like we were studying with, I forget to mention my co-authors, Yang Wang and Özlem and Jihan was visiting Arizona State University with to the tax scholarship. At that moment, Özlem was doing her PhD, and her husband Jihan was doing postdoc, and I was happy. I also had a visit to Arizona State University, Yang Wang. Okay, so we all collaborated on this model, and they are, by the way, Özlem and her husband currently working at Karabük University. So it was a joint project, and we've seen that this data, like the fitting could be improved. We immediately like published this, wrote this paper and published it. But when it comes to the time series or other models, it is possible, of course. It is possible to consider in the future studies, and data here is available from. So here, I think I forget to mention from Burchulovsky. Süreyya Hocam, Burchulovsky published this model with, after. Did I mention about Nur-Sultan? No, I happen to forget about this. Okay, so we have limited number of patient data, and Burchulovsky published this made it public after, of course, passing this all ethical issues, and they identifying the patient names. Okay, so you just have patient 1, patient 2. And they are according PSA level data. So but that is somehow limited to some 100 patients or so. So I'm not quite sure if this is enough to do machine learning type of
it's not enough.
prediction,
Yes,
because
yes,
it's too low. But if you like to apply like a machine learning model, we could collaborate then perhaps with some sort of a hospital which have larger data set, and then we have to pass through this all ethical like bureaucracy. They then find data, taking the patients and so on. After that, I think it would be possible to apply machine learning models. I'm not, from my side, I'd like to say that I'm not an expert in machine learning, but I know that I mean, if you have like patients like 2,000, 10,000, then I mean, it's a good way to test if and compare with the existing fractional models or even PD models, the data if they are doing well. So this is all about the future works, and I'm excited. Of course, I'd like to continue in this direction. But as I said, the number of data we had from Burchalovsky is very finite. Okay, so I'm not quite sure.
Yeah, you said that memory included. So there in your graph there are the days. So this belongs to just one patient of time series data. So for 100 patient, is there a time series data of each 100 patient? Then
yeah. To that memory effect. So when it comes to by memory effect, we are saying that we are taking each patient individually. Okay,
individually.
So, yeah. So we think that like each data, like when it's treatment on and off, it's going to affect the previous step is going to affect the future steps. So this kind of memory, I would say, okay, is present in this kind of data. So we said should be like either delay model, which is not easy to analyze in our case. So I'm talking how we decided to jump to fractional model. So we said, okay, the fractional could be easier to analyze compared to delay model. So that's how we end up with this model.
Can I ask question?
Sure.
Ardak, can you open this system of differential equations?
Okay. So this one or this one?
Yeah, it doesn't matter, anyone.
Okay.
You see this one, okay. Now you see this, you are considering system of partial differential equations with fractional order, right? And your numerical results, of course, will depend on how you are choosing this alpha 1, alpha 2, etc., right? So right. I wonder how you are choosing these numbers. This is first question. And some idea is that to determine this order of fractional differential equation, it is well known inverse problem. And we have done a lot of job in this. Recently, I have published a paper for system of differential equations, how to determine this alpha 1 and etc. with Professor Umar. It is in fractional calculus and applied analysis. It is just this year it has appeared. So I think it is interesting to know how you are choosing this alpha 1, alpha 2, because if you choose them near 0, your numerical result will be different. If you choose alpha 1, etc., near 1, then completely different result. So how you are going to choose this alpha 1, etc.?
Okay, that's a indeed very good question again. So the numerics part of this is we got a lot of help from Jihan. He's a computer science guy. Okay, so so the most of the part of the numerics was carried out by him, but what I happen to know is he followed Adams, Bashford, Moulton numeric scheme algorithm to write the algorithm for fractional order models. And when it comes to these orders of these alphas, as you say, this is the most difficult part when it comes. So the fitting was like we were like applying this. The aim was to minimize this mean square errors, and then what I know from my side is that they use the ready package like some sort of FME search, which I'm not aware of. So perhaps this could I could so I don't have exact answer to your question, Professor Ashurov, but I can ask this to Jihan and get in touch with you. Okay, so I know this wasn't easy.
But anyway, what is your alpha in this research? I mean, alpha 1, alpha 2, alpha 3. In your research here, what numbers you have chosen?
Alpha, yeah.
Yes, I didn't include them, right. So this is, I think we have in our published paper, which let me check this, and after the talk, if it does include alphas, I can send you by email.
Okay.
If it doesn't, and I will ask Jihan about these details, and I can send you by email. I'm sorry,
okay.
I couldn't answer your question right now.
Okay, thank you very much.
Thank you.
So, do you have question now? Thanks, Ardak. Very nice talk. Maybe advance, maybe discuss. You are welcome. No question, no. So thanks for your
Professor
attention.
Ashurov, thank you very much for organizing the seminar series so beautifully. And I'm very happy that one of my young professors attended my course, gave such a perfect lecture today. So I'm very grateful. Nowadays, Professor Ashurov, the young people are more successful than I, more popular. So thank you very much for giving me the chance to see you and the young people again. Thank you.
Thank you.
Really, thanks for you and Bülent Karasözen. If you remember, you opened Institute of Mathematics also for me during the 10 years. So,
that's right.
Yeah, Professor, I remember very well.
Yeah.
Professor.
Thanks.
It was my pleasure. I'd like to thank all the organizers of this seminar series. Yeah, indeed, like we can continue our collaboration from this. We can know each other better during the seminar talks, and we have new collaboration possibilities for our future studies. Thank you indeed for organizing.
Professor Ashurov.
Yeah.
Professor Ardak, maybe I can tell you, if you check in internet, maybe you could consider to also use a stochastic differential equation.
Sure. This
you
is
can
also
look at my work.
subject.
I have some works in that, and maybe you can try to benefit, including jumps also.
Yeah,
you can check some of the papers I did with Turkish young people.
Thank you.
Yeah, it is nice. Also, problem with delay here a lot, maybe problem in the future.
Yeah.
That's right.
Delay.
There is work by Emil Savku, Professor
nice.
Savku, Emil Savku with delay.
Yeah,
Okay,
sure.
Emil Savku. Okay, I'll check all this. Thank you very much for your recommendations.
Thanks, professors.
Thank you very much. We have good news also now. All video you can see from from internet, so it is nice now. Kalman's video now you can see, but next we will ask and we will put if others said okay. So thanks for my colleagues, Professor Abdullah Erdogan, who helped me solving this problem. Okay, see you.
Thank you very much.
Next week. Thank you very much.
Bye-bye, professors.
Okay.
Bye-bye, professor.
Yes.
Yes.